In this lab, we are looking at how the weight force and the drag force affect a falling object. We are also using Newton's second law to help us predict the motion of the object. By observing and analyzing the motion of this falling object, we were able to consider the different forces that were acting upon it. I recorded the falling motion of a small stress ball. In this lab, we considered how drag and gravity affect the motion of our object. I found that by considering these two external forces on the ball in my computer model, the model was able to replicate the observed data pretty accurately. As the tracker video shows, I started recording my data with the ball at rest, and then stopped recording data right before the ball hit the ground. The ball was moving in the negative y direction on my axis, and I used the diameter of the ball, which was 5 centimeters or 0.05 meters, to calibrate the measurements. I then used data from Tracker to input my initial velocity, position, and delta t into VPython. There were two different models for this lab. The first considered the weight force as the only force acting on the ball. The weight force was found by multiplying the mass of the ball times the negative force of gravity and the unit vector j hat to make it into vector form. This is a negative force because the force of gravity on the ball is acting in the negative y direction. This was the only force contributing to net force in Model 1. We then used Newton's second law to update velocity as well as position in our model. When we run this model, you can see that the ball is moving in the negative y direction, and the only force acting on it is weight force, shown by the yellow arrow. The second model considered both the weight force and the drag force. Weight force was calculated the same as Model 1. I then used the fact that the magnitude of the drag force is proportional to the magnitude of the velocity squared. I then found the proportionality factor B by plugging in estimated values until I got the end position that was similar to my observed data. The equation has to be in the positive direction because it is acting in the opposite direction as the weight force. Now the net force is the sum of the weight force and the drag force. As before, I used Newton's second law to update velocity as well as position. When we run this model, the ball again moves in the negative y direction, but there are two force arrows. The yellow weight force arrow as before, but also a blue arrow in the positive y direction showing the drag force. As time and velocity increase, the drag force becomes larger. Here is my graph comparing my two models with my data from Tracker. Because I use my observed data as initial conditions, all the plots show similar data towards the beginning. As I get to the middle, my data is more similar to the model without drag, and then towards the end it becomes more similar to the model with drag, which makes sense because I found B with my data. We can only use our model with the weight force and the drag force to predict terminal velocity, because the model with only weight force will continue to increase speed unless acted upon by another object. If I choose a larger time interval for my loop, I can see that velocity eventually becomes constant, where the graph becomes linear, which shows terminal velocity. You can see that right here. If you initially throw an object downward, the terminal velocity would be the same, because the weight force does not depend on velocity, so the velocity it takes to reach equilibrium would be the same. However, the object would reach terminal velocity faster, as shown by the computational model here, which uses an initial velocity. As my graph shows, my data along with my computational models were all pretty similar. If I were to do this experiment again, I would probably use a different object that might be easier to use the Tracker data on, that was bigger, as well as a greater mass. And I would also probably do it in a controlled environment, like inside rather than outside, where I had a lot of other possible factors.